Opening, getting. Spike.
I know that I was at a.
What?
As it helped, I don't know, people were really like,
Really into the conversation.
really into their food.
Yeah, it is a trick with people.
Yeah. Did you go outside as well?
Oh, I didn't actually go outside.
I'll go outside. Thank you.
There's some people braving the drizzle.
I know, I didn't think there'd be people outside, but I was at one meeting where they had off.
Yeah.
That really was interesting. So,
See one with like a proper like Christmas choral type bell. It's a drink if you don't hold it. It really is. It's a job done.
one big drum is just getting so people go.
I know like the facilities people in the office just down there do have like fire evacuation like bullhorns. So before it fails, we can
Well, we can do that, that'd be a while.
try and build the boat.
I didn't think there'd be people outside today. It's not that cold, it's just
Miserable.
yeah, I know. Sure, that up, it's also for us, it's beautiful.
No, it was nice. It was nice trip this year. Some years the one doesn't have a spring. It just goes straight from winter to summer sometimes. So I mean, having like a month and a half of actual spring is quite nice.
We get maybe a week, so. Elizabeth comes in.
The other Elizabeth.
I just got to introduce you in the session.
I'm proud of you.
There's a paper up there. Well, welcome everyone. Hopefully people will dribble in as I introduce the session. I'm Tom McGath. I'm the chair of this session. And this session is, of course, as you can read on the title there, feedback from both extragalactic and later on. And so I assume that if there's no more people coming in, I will introduce our first speaker. It's an invited talk today by Elizabeth Watkins on feedback in molecular gas in nearby galaxies. So,
Thank you. So I'm currently a postdoc at Manchester University, and today we'll be talking about how stellar feedback impacts molecular gas and future star formation. So I like to start my talks a little differently and give you the take-home messages so we know exactly where we're going. And my take-home messages are that molecular superbubbles are powered by supernovae, not a continuous injection of energy such as winds on 100 parsec scales. So we should not be blindly assuming that winds or a continuous injection of energy are powering every bubble we see. Secondly, I will have hopefully convinced you after the end of this 25 minutes that star formation often continues in the shells of these bubbles, despite the presence of very powerful feedback. The dense gas remains and continues forming stars. And finally, by the end of this talk, I will have hopefully convinced you that at least on 5 megayear timescales, most of the star formation we see in these shells is not triggered, but it's relocated from the original star-forming region. So now that you've had my conclusions, let's get some context. What are superbubbles? Why do we care about superbubbles? And what do superbubbles tell us? So superbubbles are hot, expanding regions of ionized gas, which sweep up the surrounding ISM into a shell, and they are driven by feedback mechanisms such as stellar winds and supernova. We want to study superbubbles because they can reach up to 1,000 parsecs in size in just tens of millions of years, which means we can easily see where feedback is impacting the gas and how much energy is being injected into the ISM. And this is important because feedback is one of the key ingredients that we need to understand why star formation efficiencies are low in galaxies. And bubbles give us an amazing, or a very easy way to tally up all of these feedback sources. Finally, bubbles are driven by the smallest scales, the tiny little stars, but they reach up to 1,000 parsecs in size. And this gives us a really convenient bridge between the small and large-scale dynamics. Like, they get so big that they impact and are impacted by the galactic dynamics. So studying bubbles, we got this nice little bridge. So there are many ways to trace superbubbles, but for the first half of my talk, I'm going to focus on using 12CO, or molecular gas. So molecular gas has some interesting things that we can benefit from by studying superbubbles with it. Firstly, we have velocity information. This means we can get out the expansion velocity of bubbles, and we can therefore get out the ages. And with ages, we can work out how much energy is injected over time. Secondly, stars form, at least in the nearby universe, from this molecular gas. And by looking at the feedback impact in the molecular gas, we're seeing the earliest possible impact of what's going on to that gas. And so this is why molecular gas is awesome. We want to use that. But there are some disadvantages, which is CO is fragile in the presence of ionizing radiation. That means the bubbles don't get very big until they're destroyed and we can't see them anymore. So this sort of work hasn't really been done much because you need high enough resolutions to capture the bubbles, but you also need big mapping areas to get a statistically significant sample. Luckily, with the FANG's ALMA survey, which found 90 which used 90 galaxies with ALMA, we managed to now finally have, at 100 parsec resolution, we finally have the mapping area and resolution needed to finally do this work. So no talk about FANGs is complete without this slide. So FANGs stands for Physics at High Angular Resolution. It is a survey looking at the baryonic cycle of 7 nearby galaxies using multi-wavelength data. So to understand the baryonic cycle, we had 90 galaxies which have been observed with ALMA to look at the molecular gas that stars form from. Of these, we had 38 which has been observed with HST, which shows us the stars which has formed from this molecular gas. And then of these, 19 have been observed with MUSE, an IFU unit, which allows us to look at the ionized gas which is formed from the feedback. And now with JWST, we even have access to the atomic phase with 78 galaxies. So we really get a complete understanding of the baryonic cycle. So molecular superbubbles is not something which has been done much. So when I went and did this work originally, I wanted to get a subsample of galaxies which had as much information as physically possible. So I went for the subset which had MUSE, ALMA, and HST. So I looked at 19 galaxies, or 18. One of them, the metallicity was low, couldn't find anything in the CO. So I found across these 18 galaxies 325 bubbles. Now, this might not sound like a lot, especially when we've seen the ridiculous number of bubbles in JWST. But you need to bear in mind, before this work, the maximum number of bubbles we found in a nearby galaxy in CO was 4. And that was in a galaxy which is 3 to 5 times closer than the average galaxy year. But with this work, I actually found 6 bubbles in every single galaxy. So this is just an incredibly amazing result to find this many more bubbles. This meant much more statistics compared to before. And this is here. Well, I actually really love this image. This here is a representation of the 88 bubbles which we peer-reviewed to have the most beautiful, perfect, unbroken shells. So because this is novel work, we had to trust that these bubbles were real so you could trust them. So we ended up with this sample here. This is a multicolor image. We get to see the beautiful shells in orange and CO. In pink, we have the hydrogen alpha showing you this beautiful ionized gas. Then we even have some O3 from the MUSE showing you literally supernova, which are going off. And with how many green spots there are, this just is showing you just how much supernova must be going off here. And then in the HST, we have, in blue, all of the stars. And now I'm just going to fade into the CO so you can just see these beautiful shells that we found. So with those bubbles, their average size was about 130 parsec. And for every single bubble using the CO, I went and found their expansion velocity. So with that, now we have bubbles, what's next? What do we want to do? Well, the most obvious and the first thing we want to know is how old they are, to know about how much energy is injected. So since bubbles expand, or we assume they expand with a self-similar expansion, to find out their age, we just need to have their radius and their expansion velocity. And we also need this other value, eta. But you might have noticed there's a problem with this equation in that we actually have 2 unknowns. We don't know how old the bubbles are, we actually don't know what ITER is. So ITER is the mechanism which powers the feedback mechanism powering the bubbles. And normally when we go do this type of work, we just guess. We just say, oh, it's a value of a half, radiative injection of energy. But we actually don't know what this is. And if you do this wrong, you're going to get ages up to a factor of 2 wrong. But luckily, I chose a subset of the galaxies where we had HST. And this means that we can go and fit SEDs to the clusters or the associations which are present in the bubble. And this actually allows us to get the ages. So there's no guessing here. Instead, we're going to derive exactly what's powering these bubbles. And we find that the HST is 1-to-1 with the CO if we use a value of 1/4, which is the exact value you would expect if for supernova driving the bubbles. And this is my first conclusion that we've already seen, which is that on these 100 parsec scales, that bubbles, molecular superbubbles, are driven by supernovae or supernova rather than a continuous injection energy. So we should not be blindly assuming just one model. So I only found, 325 bubbles. So is that significant? Like who cares, right? If it's only that many, does it matter that, that these are the couple which are the special snowflakes? But when I actually looked at the molecular mass within these shells, actually up to 6% of all of the mass in the galaxies were in just these shells, which is just outrageous when you think of how the small number of bubbles I found. They're important for the star formation cycle in these galaxies. But that means that potentially this is 6% of molecular gas, which might be locked out of future star formation. So I wanted to understand, can this gas still form stars? And the way I did that is, the exact value doesn't matter here with the percentage, but I assumed that stars form with a 1% efficiency, and that the gas you see in the shell was swept up from the original star forming region. This means that there should be 100 times more mass in the shell than the stars in the center. And if this changes for any reason, we can determine whether the star formation can continue. If it decreases, so the efficiency looks higher, we're losing mass over time, and therefore this gas is not going to continue forming stars. But what we see instead is as bubbles get bigger, indicated by the size of the markers, and as they get older, indicated by the color, we find there's too much mass in the shell to explain the stars in the center. And it's not that the stars are forming less efficiently because they're old. This is literally saying that gas must be swept up over time. It's not being destroyed by the feedback present. So the already present dense gas is remaining, and is actually the star formation potential in these bubbles is increasing over time. And this is something we even see in the Milky Way. So this is on much smaller scales, 13 parsec scales. But it's not unusual to see that when dense gas is present, that feedback struggles to do anything. So this is a filament with 20 solar masses. And what is really interesting is if you look at the virial, I don't know why the resolution's over there. If you look at the virial ratio along this filament, it's actually not obvious where there's O stars. There's only O stars in the bottom, but the virial ratio is kind of consistent. And the reason it's like that is it's so dense that the feedback does nothing, or it doesn't stop the star formation. So it's not that unusual to think that when you have dense gas, that feedback struggles. So the CO work is not as the work I'm as known for, but that was the work I originally started. Then July in 2022, COVID times, the years blend. During that time, this image came out, one of the first images we've seen from JWST, and it's just absolutely breathtaking. We got to see all this beautiful, fluffy structure showing you all of the dust, or all of the stuff that can form stars. But what I noticed immediately is that there are bubbles everywhere. And I like to think that this image really captures how I felt, right? The excitement of seeing all the ways that we can quantify feedback in just one image. But then it quickly became Woody's face, which is, if we're going to do that quantification, we need to count every single bubble that we can see. So yeah, but I wanted to quickly, why are bubbles so visually apparent in this data? So what we're looking at are polycyclic aromatic hydrocarbons, mouthful, PAHs, and PAHs are, they emit because of stellar light, which is everywhere. They twist and they bend, and so what we're getting is a really, whenever there is PAHs, you will see it. Very cancerous, by the way, these things. You get them in barbecues, so we get them on Earth, but all of our stuff in astronomy is quite poisonous, like CO as well. Yeah. So you have your PAHs, and there's starlight everywhere, and so it shines. But PAHs are destroyed when you have strong UV, which bubbles have in abundance. So you end up with a massive decrease in the center. But because there are more stars, you get a massive increase in the intensity in the shell, which is why these cavities are so visually apparent, why it's so easy to see them. So as I alluded to, we had to find the bubbles, and that is what I did. Very similar to the CO. I just replaced the CO with JWST. So I used Muse, JWST, and HST. I went and by hand counted 1,694 bubbles, which is very fun. I actually really enjoyed it. No, I did. Like, what would it have been if we as scientists get this brand new, fantastic image of JWST and then went, computer can do it. I got to stare at this data. I got to feel this data for a couple of days, and I just think that's so beautiful. Like, I was one of the first people to see this, and every time I think of it, I just can't help but smile. It was a really wonderful couple of days. So I went and counted these bubbles. Here they are. And on average, the sizes of these bubbles range from between 6 to 500 parsecs in radius. And what's interesting is around 31% of bubbles contained a smaller bubble in its shell. And as I alluded to with the CO, we have all of this molecular gas, and this is now directly showing that star formation is continuing in these shells. It's not being halted. But this is a very interesting implication. This is one of the galaxies, and we found 2,000 bubbles. We have 77 more galaxies. We have up to 300,000 bubbles to find. And this is just amazing, just all of the statistics that we can finally do now that we have such an amazing sample, which we will find them eventually. We're sorting out systems and science to do this. We can't have just one person to do it. It'll be here for the rest of my life. So the only sad thing about JWST is we don't have the velocity information. With our CO, we have velocities, which allows us to nicely get out expansion velocities, ages. But what we lack in that information, we gain with the power of statistics. We have 2,000 bubbles. So I went and got the size distribution of the bubbles and compared it to theory. So the size distribution is very much set by pressure, the pressure going out and the pressure coming in, and also the time scales over which you can visually see bubbles. And it results in a power law of around minus 2.7. So if we compare our distribution to this power law, it gives us a nice representation of something going on in the galaxy if it differs. And we actually found that we're a bit shallower than this power law, minus 2.2. And this could either be to do with the internal pressures, but what we need to remember is 31% of bubbles were found to have at least one smaller bubble in their shell. And what's more likely happening is bubbles are merging over time. This is again showing that bubbles are forming in the shells of bubbles. And the reason it will get shallower is if you imagine your power law, if you lose the small and you make the big ones bigger by merging, it tilts it a little bit, and that's why it's a bit more shallow. So just by looking at the size distribution, we don't even need to know that there are bubbles inside of bubbles. Just by looking at the size distribution that we have, we can already determine that star formation is clustered, that it continues in these shells, which I just think is fantastic from one plot like this. So I wanted to quickly allude to some of my new work, which is to do with actual sims. So I actually want to know a little bit more about how do bubbles actually expand? How is the ISM impacted? And how is star formation in the shells propagated? Is it triggered, relocated, unveiled? So in observations, we do not have the ability, we are not God, and we cannot do a time bar, but in simulations we can literally see how the bubble expands, which is amazing. So what I've got is a repo simulation, which I did not run, someone else ran it for me, and I went and I traced out the shells using that 3D disk method that Annie Gao talked about on Monday. So this is like more equivalent to your sort of 3D dust maps. And I went and found 88 bubbles, traced all of their shells, and we got a 5 megayear time scale with time steps of a half. And we can actually see now how the bubbles are expanding, what's happening with the star formation over time. So it might be hard to see some of these markers, but the first result, which I found really interesting, and you can see it sometimes in the observations, well, in a lot of them, is bubbles don't expand like in the center and with perfect spheres. All of our models, we typically assume a isotropic ISM and everything's in the middle, but the ISM is clumpy. And so how bubbles actually expand is you have your dense gas and you have your low density gas, and the stars are formed in that in the high density gas. It doesn't push the gas much that way, but it pushes it the other way. So you end up with a very off-centered expansion, which impacts our ability, if we're there trying to determine ages, if we're there matching up to models, we're going to get the wrong results because the expansion is quite different. Like a lot of them even end up being like these wibbly peanuts. But here we can see towards one edge is all of the sinks, but stars, and this off-centered expansion. And the next result, which I found really interesting, is I wanted to see when we have new sinks form, where are those sinks forming? And I assumed that they'd just be distributed around the shell. But what I found is that most of the new sinks or stars which form, they form really close to the old sinks, the thing which is powering the bubble. And this is interesting because what that means is that our dense gas, which is next to that star cluster, is continuing to form stars despite the feedback. And we're not actually triggering anything at all. This is just star formation, which is just continuing in our already present dense gas, at least on 5 megayear timescales. And the upper limit to the amount of stars which are potentially triggered is actually closer to 12%, because when I looked at the distribution, so on here, the black line is the radius of the bubbles on average, and then the blue line is the distance away from the sinks that the new stars formed, and they're within half a radius. They are very much staying close together. So this means that every time we see a star formation region in a bubble, we shouldn't be blindly assuming it's triggered. Some of it can be, but some of it is going to be relocated. Some of it's going to be star formation which was already happening, which just got bumped into the shell. So we need to be very careful when we are going and assuming how much star formation is triggered. Right, I actually finished a little early. I normally talk a little slower. So yeah, this is my final conclusion. And now we've had my conclusions. This will be the third time you're seeing them. So I should have hopefully convinced you at the end of by now that molecular superbubbles on 100 parsec scales are powered by supernovae, not a continuous injection of energy such as winds. We shouldn't be blindly assuming one model over another, and we need to be careful. Secondly, star formation continues in bubble shells. Despite the presence of incredibly powerful feedback, the dense gas remains and continues forming stars. And this dense gas, while it is sweeping up more gas as it goes, as we saw in the CO, this dense gas isn't brand new and fresh. It was already present from that star forming region, is pushed out the shell, and that star formation is now continuing in that shell. And only probably up to 12% of the star formation we see in a shell, we should think of that as triggered. So thank you so much for listening to my talk, and I'm happy to take questions.
Yes.
So regarding the relocation, in Arepo, is there any systematic velocity of the second generation feeds moving outwards? Do you see any evidence that that gas has been at least raised a little, like an accelerator or something?
Essentially, what I see is that it forms where that dense gas is, so it tracks along with the gas. So the stars which have already formed, like there's a little bit of a decoherence, which is normal, but the brand new stars which are the brand new things which have just formed, they are forming in that dense shell, but in the dense shell which is close to the old stars. So many questions.
Lots of questions. Yeah. Yes.
Yeah. So with this like power law you found with like the bubble like propagation, and when I think about like a talk we saw yesterday or the day before yesterday where like things in like spiral arms get like compressed, of course like things can also be torn apart. Is it possible that the small discrepancy you saw in the number is because some bubbles are a little bit like stretched out, and like you have like the on the one side the supernova driving the bubble, but also like the spiral arms that they are tearing.
It's not to do with the shear. What we're seeing, the only other explanation for the discrepancy in the power law is pressure. So it's if because the Nath et al. 2020. It assumes what it does is it uses the hydrogen alpha luminosity to get out a different parameter, and that they use that to set their pressure. And so if the pressure in NGC 628 is not the same as that luminosity function, you can also change that power law. But it's just based off the pressure pushing in, pushing out, and the how the average lifetime of the bubble. It's much more likely that what's going on here is this bubble merging process.
Good questions. Mordecai.
This 10% triggering is a number that has repeatedly been found by independent means going back at least to the 90s when Fukui's group using the big Japanese CO telescope.
Yeah.
Had already found that by looking at like CO and the LMC and overlapping with. So it's great to see this repeated, expanded with hugely more statistics in different galaxies, and the result holds up.
Thank you.
You over there? Yeah.
Me?
Yeah, you. Sorry, I don't know your name.
So my question was on your third point. How much do you think that conclusion is affected by the specific feedback recipe in the simulations?
Yes, so I didn't talk about that. So we only have, sorry, I should have said that. We only have supernova feedback. So this result is very much for supernova dominated bubbles. So if it was more of a wind bubble, or even if you had H2 regions, maybe this won't hold up as much. So take this with a pinch of salt that this is with specifically supernova. Though because a lot of my CO work, those CO bubbles are driven definitely by supernova, you can think of it more in relation to them. So it's still valid, is just, just bear that in mind.
Yeah. Bubbles are ubiquitous.
Mm-hmm.
Thank you.
Yeah, bubbles all the way down.
Yeah, we live inside a bubble.
Mm-hmm.
Yeah, called the local bubble. And some of the things that we're learning about the local bubble is that it's not one supernova, it's many, like 15. And the super bubble and the explosion, the supernovae are occurring in a pre-existing, we think, H2 region.
Yes,
So
definitely.
That adds added complexities to the picture that you're proposing.
What it does, so having that pre-clearing is really important. So in these supernova ones, what we in this sim, what I find is the bubbles don't actually get as big because the gas has been cleared out. It's still so much dense gas that the supernovas just don't do much, right? Like the dense gas is king. So that what I find is oh my God, why can I not say that word? The pre-clearing is really important to make the bubbles bigger. Without that, the bubbles end up being a bit smaller because more energy is, that energy goes first into clearing out the gas, whereas the H2 regions and the winds, that when you have those included, that energy is already put in, so you don't. So yeah, bubbles get bigger with more feedback. I should.
Okay, one last question while I switch talks, and if the next speaker could come down.
Yeah. So my question's about the selection effect. So if you have a discrepancy between the predicted and observed size distribution of bubbles. So I was wondering more about how you detect bubbles and if your detection efficiency depends on the size of the bubble.
Right. So when I did that power law and that distribution, where it's not complete, we don't use it. So that it doesn't matter. We're complete to about 30 parsecs, but also there's some simulations which say that that power law kind of stops around 30 parsecs. So we're totally complete. And if you're thinking about even personal selection bias, I had behind you 2 other people who went and who bravely volunteered, and they found bubbles, and I redid every bit of this analysis with their catalogue, and we got the exact same result. So it's independent of personal biases. So I hope that answers your question. If it doesn't, I'll talk.
All right, well, we should
Sorry.
There you go, and just switch it on when you're ready. Okay. All right, so the next speaker is Sumit Sabardakari. Where do stars explode in the interstellar medium?
Can people hear me? Okay. All right. Hi, everyone. My name is Sumit. I'm an assistant research scientist at Johns Hopkins University. And the title of my talk is Where Do Stars Explode in the Interstellar Medium? So that's kind of continuing the theme of where are stars injecting most of their energy. This is a work that I'm doing primarily in collaboration with the FANG survey, which Liz just introduced, as well as the local group L-band survey, which I'm also going to introduce in my talk. So as a reminder, why do we care about supernova explosions? Because they are the main sources of heat and momentum in the ISN. And it's a combination of this heat and momentum that drives outflows like you see here in M82, turbulence, hot gas, which provides pressure support against gravitational collapse, cosmic rays, which are accelerated by supernovae and in principle can do all of the above. Metals that are synthesized in stars get swept up in blast waves all the way out to the circumgalactic medium. And the supernovae play a small but not dominant role in the destruction and dispersal of molecular clouds along with photoionizing radiation. So supernovae are really important for the regulation of star formation, but a critical and I would say kind of an overlooked factor in the efficiency of supernova feedback is the ambient density distribution around most supernovae. And to illustrate this point, here's a simulation by the SILK collaboration. This is a vertical slab of the interstellar medium with density and temperature. And I'm showing 2 iterations of the simulation. On the left is both simulations are the same. The only thing that's changing is the location of the supernovae with respect to There we go. Okay. With respect to the gas clouds, these are random, and then here the supernovae are correlated with the gas cloud where they are born. And you can see that the ISM looks completely different in both cases. On the left, you have an ISM that is really thick, lots of overpressurized hot bubbles, lots of hot gas, lots of hot outflows, and on the right, it's a completely different looking ISM that is very thin, very little outflows, very little hot gas, lots of diffuse warm gas, and very peculiar molecular clouds. So the same simulation, but just changing the locations, you get two completely different interstellar disks. And the basic reason here is that astrophysical plasma cooling is highly density dependent. Okay, cooling rate goes as density squared, and so the distribution of densities is really important to understand. But this is also really uncertain to actually predict where they're going to explode for a number of reasons that have their own uncertainties. For example, stellar lifetimes, right? How long does a massive star actually last? Okay, most massive stars are in binaries. You can have mass loss, interactions, common envelopes, and so the lifetime of a 10 megayear star could be 5, a 5 megayear star could be 2, and we really don't know that very well in the stellar astrophysics field. Then you have kinematics, all right? A star is not going to remain inside the star cluster. It can get kicked out by binary interactions, by, n-body interactions, supernova and a binary explosion, and these things are not captured in a lot of galaxy simulations. Finally, how long does a dense gas cloud remain dense? How long does it actually last? If star formation starts, it quickly disperses, but then there's a lot of other processes that can determine whether that cloud remains for a long period of time. So these are all big questions in their respective areas, and people are working on it, but I'm an observer. What I'm trying to figure out is what's the best way I can help, and I feel like a great thing that I can do is just give you a census of where stars are exploding from observations. And the reason we can do this now is because we're really in this golden era of interstellar surveys in our nearby galaxies. We really have now the ability to map all of our nearby galaxies from millimeter all the way out to X-rays, mapping each phase of the multi-phase ISM down to interstellar clouds, down to individual H2 regions, down to individual supernova remnants. And so we're doing this with the FANG survey, as well as the LGLBS survey, and really the goal is to just take every telescope and just point it at every galaxy within 20 megaparsec. We're not quite getting that much coverage, but we're getting quite a lot. So with this data set, we have a fantastic statistical and wide range of environment survey where we can look for the dense gas distribution around supernovae. And this is something that we pursued with Nessmaker Chen, who was a PhD student at Ohio State. This is the first time that we did a molecular gas survey at the typical scale of a giant molecular cloud, which is roughly 100 parsec. So this comes out of the FANG's ALMA survey, which you saw in Liz's talk. This was 90 galaxies observed with ALMA CO2-1, and there's about 63 supernovae that have gone off historically in these galaxies. And so what Ness did is just kind of looked at the locations of these supernovae, what the gas density is. Okay, so I encourage you to look at the two papers that Ness wrote, but the long story short is that we find that 50% of type 2 supernovae are not coincident with giant molecular clouds at the scale of 100 parsec resolution. So this is the first time that it has been empirically shown directly with supernovae that there is a substantial fraction happening outside of molecular gas. And this could be happening because the stars disperse from their birth sites, or maybe the pre-supernova feedback or prior supernovae are clearing the gas. That remains to be fully determined. But we realized that if we wanted to kind of build the statistics, there are two inconveniences. One is that supernovae in the local volume are just rare. We're working with a 63 sample of supernovae, and that's just not something we can get around. It's just we're limited by that at 20 megaparsec. The other problem is that we were only looking at the molecular gas, but there is a lot of dense gas in the atomic phase as well, and it's also a substantial fraction by volume. But you can't really get it at the same resolution as molecular gas because it is obtained from the longest wavelength, 21 centimeters. So by definition, it's going to be low resolution. There's nothing you can do about that. So up until the square kilometer array or NGVLA comes up, the best place to get local group, the best place to get atomic gas maps are in the local group. And this is exactly what we are doing with the local group L-band survey. This is a 2,000-hour VLA survey of 6 northern local group galaxies, including M31 and M33. And the goal, which is in a paper that we have submitted recently, is to map the atomic ISM down to 20 parsec resolution. This is going to be amazing spatial resolution and Milky Way-like velocity resolution as well. So with this survey, we can now look at, before that, I should mention that these atomic gas maps are available, but if we want to look at the atomic and molecular gas around supernovae, the problem is that there's no supernovae in the local group. So how to get around that? I came up with this idea that instead of supernovae, you can use future supernovae, i.e. evolved massive stars like red supergiants and Wolf-Rayet stars. So red supergiants are the core helium burning phases of 8 to 30 solar mass stars, and then Wolf-Rayets are the evolved burning stages of more than 30 solar mass stars. And why are these great substitutes for a supernova survey? Reason number one is that we have seen in pre-explosion images that these red supergiants do explode as type 2 supernovae. The connection between Wolf-Rayets and supernovae is a bit more dubious, but these are the next stars in line to explode in M33. Secondly, these are all evolved. They only have about 500,000 year to 1,000,000 year left, so they're going to explode very close to where they're currently located, maybe plus minus 10 parsec if you account for drift, but that is the resolution of our ISM maps. So these are good instantaneous locators of supernova. And then finally, there's thousands of them per galaxy. So now we don't have to worry about 63 supernovae. We can work with 1,000 in just one galaxy. So with this approach, with one of my former REU students, Jordan Wagner, we decided to correlate the red supergiant and Wolf-Rayet catalog in the local group, which has been painstakingly put together by Philip Massey and collaborators from lots of ground-based surveys in this atomic gas map from the LGLBS. And we are also concurrently doing an ALMA survey of molecular gas at the same resolution in the central 3x5 kiloparsec. So this is what we get eventually, and I'm happy to talk about this in more detail during the break. But what I'm showing here is the cumulative distribution function with the gas surface density of molecular hydrogen and of atomic hydrogen. You're probably used to seeing CDF going from 0 to 1, but here it trails off at a limiting fraction, which is the fraction of the sample below the completeness limit of our gas survey. So the takeaways are, number one, that more massive stars are exploding in denser gas, okay? I probably should have mentioned the purple is the Wolf-Rayet and red is the red supergiant H2 distribution. More massive stars are in denser gas. But there is a substantial fraction of these massive stars that don't have any molecular gas around them, okay? It's as big as 72% in red supergiants, and it decreases for the most massive stars up to 44%. And this is, again, kind of going into the previous idea that there's gas clearance happening around the supernova sites, or maybe the stars kind of drift out before exploding. There's a similar story with the atomic gas maps, but the peak of the gas density is much shorter compared to, or sorry, narrower compared to the molecular gas. But still, if you look, for example, at sigma of 10, there's half of Wolf-Rayets that are exploding at densities above that, and only about 20% of red supergiants that are exploding above 10. The distribution that you see is not random. Okay, we're looking at 2D correlations, but if you take stars randomly and put them in this map, that distribution looks like this purple area, and you can see that our Wolf-Rayet mass distribution is very different compared to that. The shaded region is the 95% confidence region. And again, if we randomly distribute the Wolf-Rayets according to, let's say, the H alpha, we can reproduce what we see in the observation. So again, if you do 2D correlation, there's always going to be some random component, but we do have astrophysical information beyond just random correlations. Same thing with red supergiants. If you just divide the red supergiants into luminosity brackets, you can kind of divide them by mass. And we can see that the highest mass red supergiants, 15 solar mass and above, they do go off in higher densities than the lower mass red supergiants, which essentially becomes indistinguishable from random. And then you can also see this in the spatial distribution. This is the atomic gas map in gray, the molecular gas and contours, red supergiants and Wolf-Rayets as red and purple. You can see the red supergiants are kind of distributed in the field, but then if you look at some of the high mass star forming regions like NGC 604, IC 142, 595, you see the Wolf-Rayets are densely concentrated in the center where the dense gas is, and then the red supergiants are kind of outside. So in the last few seconds, I just wanted to mention some of the other directions I'm thinking about. So I think this is a very cool thing to actually compare with what we get or what we're putting in galaxy simulations in the feedback models. Okay, but a couple of interesting things to think about. Number one is that if we're just correlating stars with gas, then we just get the correlation. But if we want to know, for example, is this supernova, when it explodes, is the blast wave actually going to interact dense gas or not? That is something we can do with a JWST survey of supernova remnants, and this is something we did in a 2024 paper where we actually looked at infrared signatures of interacting supernova remnants, and we found that about 14 to 42% of them show infrared signatures, specifically molecular hydrogen. We're doing an expanded red supergiant survey in our nearby galaxies to actually see how this spatial correlation of massive stars and ISM deviates for lower mass galaxies and higher mass galaxies, because there will be some dependence on the gas clearance there. And then finally, if you go to higher resolution, you can get more information. This Wolf-Rayet star in our ALMA map is next to a molecular cloud, but then we have this little patch of the galaxy where we have 20 times better resolution, and we see that the Wolf-Rayet is actually in a cavity and not actually hitting the molecular cloud. All right, so lots of things, very exciting direction, and I'm going to leave the results up here and take more questions. Thank you.
I have the exact same questions last time about the selection function and more obscured regions. So if you're trying to count the fraction of stars that are supernovae that occur in obscured regions, are you worried that you might not see stars in molecular clouds?
Yeah, so that's a good question. So M33 has been pretty much surveyed really nicely with a wide range of telescopes in optical and near infrared. And I think the conclusion there is that we're not really missing a whole lot of stars because of extinction, maybe one or two at most. The number of stars also correlate with the local star formation rates. So I think that's fine. In a galaxy like M31, it could be a problem because there's more dust lanes you're seeing through.
Yeah, how does the number, just the sheer number of Wolf-Rayet stars and red supergiants that you see in this galaxy, how does that mesh with the star formation history and the fact that we don't have any supernovae that have gone off recently?
Yeah. Yeah, so the supernova rate is once every century, so that you're just Poisson limited there in principle. The red supergiants and Wolf-Rayets, I think so. I don't think there's published work on this technically. This is something I was planning to do, but some of the back of the envelope estimates that I've done, like in NGC 604, for example, you have 11 Wolf-Rayets. That's consistent with the local star formation rate there. So, but then a more expanded work throughout M33, that's TBD. Yeah.
Monica.
So in the Milky Way, Yusuf Sada et al. Back again many years ago used masers to trace the interaction of supernovae with dense gas, and they got 15%, which it's interesting that it's so consistent.
Yeah. I think I really want to prove that the fraction is not zero, which I think is something that comes out in a lot of simulations.
No, it's not zero, but it's also not large. And
right, yeah.
You just blindly place supernovae on dense gas, you get large.
Right, yeah.
One last question.
Probably a really simple one. Obviously, you're doing this in projection, and there's a large fraction of the subtended angle that is out of the plane where these things could go if there are binary interactions or whatever. So how much do you expect that to decrease the fractions that are associated with dense gas if you had the full 3D information?
Yeah, that's kind of what I was getting at here, which is that, yeah, like there will be always there will be a fraction that is basically due to random projections. But at least for stars above 12 solar masses, which is the relevant timescales for, let's say, molecular clouds, you do see a separation from this random component. So if you basically take 12 solar mass stars and above, you will be able to like distinguish, like, you know, let's say like separation due to binaries or like pre-supernova feedback and other type of stuff.
Okay, well, let's give our speakers.
All right, it's time for some flashbacks. Sorry, that's a great point. Let's do some discussion.
Yeah. Adam?
I thought I got the schedule wrong.
It's okay. It's been a long day. Okay, everyone. We're gonna start our discussion, but before we move into discussion, just a quick conference announcement to please submit your hack day ideas for Friday. I didn't have to change this slide today. It made me very sad. There were no new hack day submissions. So it's the same stuff that we had yesterday. So we would love to hear your ideas. So you can use this QR code to go to the form, or you can go to the links on the website or the Slack channel. Okay, thank you all. So we're gonna have discussion. Adam, do you wanna?
Yeah, sure. Yeah, absolutely. So we have 3 more discussion topics today. We did merge one of them, I think. So the all about dust discussion, which Chris Clark is going to lead. This is merging a few different questions. And the second one is the physical resolution needed to get the ISM right in other galaxies. And so Becca Levy's going to lead that one. And does the Milky Way really have spiral arms? Sarah Lohman has graciously decided to lead that one as well. So we're going to do it a little bit differently today. We're not going to assign rooms, so we're kind of trying to get some level of interest in each of these before we decide where we're going to send you, so that we don't overflow Cafe Con like we did yesterday a little bit. So could I get like maybe a raise of hands who's interested in the first topic about dust?
Oh, wow. Cool.
Okay, decent size. All right. How about topic 2 with Becca? Okay, more. And then the third topic with Sarah. Okay, great. I think then that topic 2 we're going to keep in here because it's the biggest group. And then let's say, Chris, you guys can go to, do you have a preference? Equal-sized groups?
Cafeteria.
Cafe, yeah.
Cafeteria.
All right, cafe.
I'll write that down real quick.
And then Cafe Con for the third topic with Sarah.
Oh, no, I can't write it down. God damn it. Let me know if you have questions. I can't edit in real time.
Oh, yay. That's fine. That's fine.
Okay. Thank you so much, Tom. You killed.
Yeah, I wish I realized. I saw that.